Combination problems are a little bit different than permutation problems. In combination problems, we are no longer interested in the arrangement of objects that we select. We are simply interested in a group of objects selected from the set. Once again, another clue that might help you in certain problems is keeping in mind that the number of combinations given a certain set size and certain number selected, the number of combinations is always less than the number of permutations. Again, let's refer to my word diagram, and you can see that we calculate combinations. We use the same sort of nomenclature, but the equation is a little different. Combinations are calculated as n factorial divided by r factorial times the quantity n minus r factorial. And once again, for those of you with a fancy calculator who might do these calculations for you, you're looking for a PRB, probability key, or a key that says N uppercase C R. And then all you have to do is punch in the N and the R, and it will calculate the number of combinations for you. Okay, let's jump right to a combination problem. And in this one, we learn that 6 people are eligible for a drawing. I don't know what they did to earn eligibility, but they are. Each of them is going to win $1,000, and we want to know how many ways 3 winners can be drawn. Well, first of all, again, the trick in these problems is to determine whether it's a permutation or a combination problem. And in this case, does it matter the way that we is the arrangement in which we choose the 3 winners important? Well, no, they're all gonna win $1,000. It doesn't matter if we pick A and then E and H or H, A, and E. It doesn't matter. And thus, we're looking at groups of winners, groups selected from the set, and we are interested in calculating the number of combinations. So in this case, we need N and R. What is N? We have 6 people eligible for a drawing. N is 6, that's our set size. How many are we selecting? We're going to select 3 winners. R is 3. And so now C N comma R is equal to N factorial, 6 factorial, divided by R factorial times the quantity N minus R factorial. And now we can do some simplification. We have 6 factorial divided by 3 factorial times 6 minus 3 is 3, another 3 factorial. And now we can begin to write things out. Okay, I'm doing a different problem over on that sheet of paper, so let's do it. This would be 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 3 times 2 times 1. And once again, everything is multiplied together in both the numerator and denominator, so we can cancel like terms. We can get rid of a pair of 1s, a pair of 2s, and a pair of 3s. And what are we left with? 6 times 5 times 4 divided by 3 times 2 times 1. Didn't I do this problem somewhere else? Maybe not. 6 times 5 is 30, and let's see, that's 120 when you multiply 30 by 4. Divided by 3 times 2 times 1 is 6. And let's see, 6 goes into 120 an even number of times, doesn't it? 6 goes into 12 twice. So we got 20 different combinations, 20 ways that we can choose 3 winners from a group of 6. And again, let's just take a peek here. Let's say we have A, B, C, D, and E. 1, 2, 3, 4, 5. I better put F in there as well. And now let's say one of the groups we chose was A, C, F. Is it possible that another group could be F, A, C? No, that is not possible. These are the same groups. Recall, order of elements does not matter in a combination.